Alright, so now let's go ahead and define the inverse for the secant, the cosecant, and the cotangent functions. Beginning with the secant here, we have y is equals to the secant inverse of x if x is equals to the secant of y, where the conditions are here that the absolute value of x has to be greater than or equal to 1, and the restrictions in the domain for the secant are that the inputs have to be between 0 and pi. 0 and pi being allowed it to be included. Now, there is also one condition here that the y cannot be equals to pi over 2. Now, in the case for the secant, we have here that y is equals to the cosine inverse of x if x is defined as the cosecant of y with the following restrictions. The absolute value of x is greater than or equal to 1, and the y values have to be greater than or equal to a negative pi over 2 and less than or equal to a pi over 2. With the condition here being that y also cannot be equal to 0. Now lastly, we have that y is equals to the cotangent inverse of x if x is equals to the cotangent of y, where x is all real numbers and the y is restricted to be greater than or equal to 0 and less than or equal to pi. Now we won't be going into much detail with this inverse strict functions. They are not that commonly used, but it is still worthwhile to go over the definitions and one or two examples. So let's take a look at, let's say, one example. Let's see if we can go ahead and find out what is the exact value of, let's go ahead and pick the cosine inverse of rad 2. In other words, what is the angle whose cosine value is rad 2? Now, in this type of problems, there's a couple of things to consider. If you're planning on using your graphing calculator to get an answer, it's not really possible because your calculator doesn't really have the inverse secant, the inverse cosecant, and the inverse cotangent functions. So we have to do a workaround. And the first thing to do is to rewrite the problem without the inverse cosecant. Now, how do we do it? Well, I'm going to go ahead and set the cosine inverse, the cosecant inverse of rad 2 as alpha. Now, I'm going to go ahead and take the cosecant of both sides. Okay, now we get to see here that the cosecant and the cosecant cancel, and now we're left with simply the cosecant of alpha is equals to rad 2. Now at this point, we can go ahead and manipulate the equation further by rewriting everything in terms of sine, cosines, or tangent, depending on the problem. In this case, since we're dealing with a secant, I'll rewrite this one here as 1 over the sine of alpha equals to a rad 2. Now, isolating the sine of alpha is going to give us the following. Sine of alpha is equals to 1 over rad 2. Rationalizing the denominator, we're going to get that sine alpha is equals to a rad 2 over 2. Now we can figure out, okay, well, what was this angle alpha? Now, based on some of the examples that we did with the arc sine, we get to see here that, okay, well, the angle whose sine is rad 2 over 2, that is in between the negative pi over 2 and pi over 2, is pi over 4, or 45 degrees. Now again, you could have rewritten the problem as alpha equals to the arc sine of rad 2 over 2. Either way would have worked. So again, guys, when you're dealing with the inverse of the reciprocal identities, the first thing to do is rewrite the problem without the cosecant, secant, or cotangent inverse, and then rewrite in terms of sine, cosine, and tangent. Then it becomes a much easier problem to deal with, and then you can just go ahead and use the inverse trig functions, or alternatively, just come up with the answer on your own or using the unit circle. Alrighty, so this was a rather short video because again, we're not going to be focusing too much on the inverse of the reciprocal identities. See you in the next video, where we will be using the properties of inverse functions to find exact values of certain function compositions.